All right, let's take a look at number one. All right, the person has a balloon with this volume at this temperature and this pressure. What is the pressure when she finds this is the new volume and the new temperature? Looks like we're going to be using the combined gas law here. So let's just go ahead and substitute these values in and see what we've got here. P1 is going to be 762 torrs times the V1, which is 1,200 milliliters, divided by T1. Now you got to remember, you cannot use 25 because it's in Celsius. You have to add 273 to that. So what that's going to give me is 298 kelvins, and that's going to equal, let's see, well, we're looking for P2, so right, P2 times V2, the new volume is 1486 divided by T2. Now T2 is 15 Celsius plus 273, and what that gives us is 288. So now I have to undo what's being done to P. So what's being done to P? Well, P2 is being divided by 288, so I have to multiply the side by 288. And then P2 is also being multiplied by 1486, so I'll have to divide both sides by 1486. And what that's going to give me is P2 equals 590 torricellis. Number two, let's see what we've got here. We have a scuba diver. 40 meters is distance, and if you notice, there's no distance in gas law. So although it's interesting that she's 40 meters deep, which by the way is a very dangerous depth to scuba dive to, that's irrelevant. What is relevant is the pressure is for atmospheres, and the air she blows has a certain volume. And we also know what the temperature is. So it's looking like we're going to be using the combined gas law again. So let's just substitute in the before values. So what we've got here is, let's see, the P1 is 4 atmospheres, or 4.0, according to what we were given, times the beginning volume. The V1 is 184 milliliters, divided by, let's see, now the temperature where she blew it was 4 Celsius. Here we go again. Add 273. Again, tired of hearing me say that, aren't you? Add 273. Add 273. Add 273. What are you going to do? You're going to add 273. Turn your Celsius into kelvins. And when we add 273, what we get is 277. Equals, well, let's see what we've got now. We're looking for the new pressure is 1.1. We don't know what the new volume is. That's what we want to find. And we have to divide it by the new temperature, which it's in Celsius, so I'm going to add 273. And when I add 273 to that, what I'm going to get is 303. So in this case, what I have to do is I have to undo the two things that are being done to V2. V2 is being divided by 303, so I'm going to multiply this side by 303. And it's being multiplied by 1.1, so I'm going to divide by 1.1. And what happens when I do that is I get a V2 that equals 731.89, which for reasons of significant figures I'm going to round to 730 milliliters. Alright, let's just give ourselves a little room here and take a look at number 3. So number 3, I see I have this much volume at this pressure and this temperature, and I was asked how many moles of molecules. So I'm looking for the number of air molecules. So in this case, I'm going to be using the ideal gas law, which is PV equals nRT, and let's just try substituting in here then. Alright, so our starting pressure in this case was 304 atmospheres times the starting volume, well, just the volume, which is 5 288 milliliters equals the number of molecules is what we're looking for. And now we have to use R. R is what we call the ideal gas constant. It basically is just a correction factor that allows us to use, in this case, it's going to allow us to work with milliliters, atmospheres, and we'll have to turn that into kelvins. And so it varies, if you don't have to always use milliliters and atmospheres, but that's what we're using, so we're going to have to use a particular R value. And we're only going to use one of them in this class. When you get to chemistry, AP chemistry, you can work with the other ones. But let's just see what it is. In the case of this one here, it's 82. It's a constant, so it's always equal to 82 as long as we're working with a volume measured in milliliter and pressure measured in atmospheres, and of course temperature measured in kelvins, which it would have to be. But so we're only going to use 82. So let's just go back down and take a look at what we've got. Alright, so in this case we're going to go ahead and put 82 here for R, and then we're going to of course have to remember to add 273 to 20 degrees Celsius, which is going to give us 293. So now I have to undo what's being done to N. So N is being multiplied by 82, and it's being multiplied by 293. So that means I have to divide this side by 82, and then divide it again by 293. And when I do that, what I will get is the number of molecules in this container equals 7.4 moles. Alright, let's try number 4. Let's see what I've got here. I've got milliliters. Oh, I got moles. As soon as I have moles, I know I'm using this equation here. So let's just start substituting into this. Let's see what we've got here. We have got, let's see, the P is what we're looking for. So we're looking for P. The V is 2,500 milliliters equals N, in this case, is 235 moles times R. R is a constant, and the gas constant for us is always going to be 82 times the temperature, which is in Kelvin. So I'm going to take 15 degrees Celsius and add 273 to it, and when I do, what I will get is 288. So now, basically, what's being done to P? Well, P is being multiplied by 25,000, so I have to divide both sides by 25,000. And when I do that, I'll find that the pressure, in this case, equals 220 atmospheres. And I know it's atmospheres because this value for R yields volume measurements in milliliters and pressure in atmospheres. Let's try number 5. Number 5 says we've got milliliters and temperature and pressure and a new temperature and a new pressure. Well, this is the combined gas law. So let me just write that down real quick. Alright, so I got P1 V1 over T1 equals P2 V2 over T2. Let's start substituting in here. So P1 is 780 torrs. That's a 0, not a 6, times V1, the starting volume was 640 milliliters, divided by T1, which is 22 plus 273 is 295. Now that's going to equal the ending pressure, which is 8,200 torrs times V2 divided by T2. Now T2 is 4 degrees Celsius. 4 degrees Celsius plus 273 is 277. So once again, I have to undo what's being done to V2. V2 is being divided by 277, so I'm going to multiply both sides by 277. V2 is also being multiplied by 282, and the opposite of multiplying is dividing, so I have to divide both sides by 8,200. And when I do that, what I will find is V2 equals 57 milliliters. Number 6 asks me, well, I see the word moles, so I know I'm using the ideal gas law. So PV equals nRT. Have you asked your parents if they know that one yet? Because I bet you they know. If there's one equation other than E equals MC squared that people remember, it's PV equals nRT. But let's just try substituting in here. Let's see. P is 207 atmospheres. And the volume is 1,200 milliliters equals the number of moles, which is N, is 3.2 moles times the R value, and for us R will always be 82, times the temperature, but remember that temperature is in kelvins. And so what we got to do then is we have to undo everything that's being done to T. T is being multiplied by 82, so we have to divide by 82. It's being multiplied by 3.2, so I have to divide by 3.2. And when I do that, what I'll find is that the temperature equals 946.64. I'm going to round that to two significant figures, and so it's going to give me is 950 kelvins. Alright, let's finish off this homework. Alright, oh, I love Bernoulli's principle. Okay, so what we got here is this situation. We have an airplane wing, and the air is flowing this way, and what happens is when it reaches the wing, the air on the top has to go a greater distance than the air on the bottom does. And since it's going a greater distance in the same amount of time, that means it's going faster. So you find is the air on top is fast, and the air below is relatively slower. Now Bernoulli's principle says that fast air equals low pressure. So because the air is fast on top, the pressure is low, and because the speed is low on the bottom, the pressure is relatively high. And so what we find is pressure is what determines what happens to this airplane wing. Since there's high pressure on the bottom and low pressure on the top, this airplane wing is going to be pushed upwards by this pressure difference, and that's what holds airplanes in the air. As long as there is a significant difference in speed between the top and the bottom, there'll be enough difference in pressure to push the airplane wing upwards.